Hi, my name is Lucas Mancilia. I'm a PhD student at the Research Institute for Signals, Systems and Computational Intelligence in Santa Fe, Argentina. In this video, I'm going to present our work about domain generalization via gradient surgery. Traditional machine learning models assume that training and test data come from the same distribution. However, in real life, training and test conditions may differ by several factors, posing serious limitations for translating these models to real-life problems. Domain generalization refers to learning a model with data from different but unrelated source domains and then applying it to a new target domain. The problem itself is highly challenging since we have no access to the target domain during training. In image classification, domains may contain different visual representations like photos, paintings, and sketches. So the main challenge is how to guide the learning process in order to capture information that is relevant to the task and invariant to domain shift. In this work, we focused on gradient interference in domain generalization. We measure how similar the gradients are within and between domains by cosine similarity, considering pairs of gradients from the same domain and from different domains. As we can see in the figure, when training with multiple domains, the similarity between gradients coming from the same domain, shown in red, is higher than between gradients from different domains, shown in blue. Thus, there is information which is specific to individual domains but irrelevant to the others, including the target domain. To reduce such interference, we propose a gradient agreement approach based on the surgery strategy that operates on the set of domain-specific gradients during the optimization process. We aim to modify a standard mini-batch gradient descent by incorporating a gradient surgery step before updating the network weights. Given a set of n source domains, we want to minimize the average loss over all source domains. During a training iteration, we sample a mini-batch from each source, perform a forward pass, and compute the domain-specific gradients. To measure the agreement between these gradients, we define an agreement function that checks element-wise if the signs of the gradient components match or not. The next step is to build the consensus gradient that will be used to update the model parameters. To this end, we propose to retain the components that agree and modify the conflicting ones. We propose two alternatives. The agreement sum methods set the gradient component to 0 when there is no agreement. This strategy avoids updating the weights when there is no consensus. The agreement run strategy assigns a random value to the gradient component when there is no agreement. In this way, we can prevent the effect of having dead weights that never change during training. By means of gradient surgery, we aim to adjust model parameters by modifying gradient update so that they point in a direction that improves the agreement across all domains. We compared our method with DeepAll, a baseline trained with multiple domains using the standard setting. The PCGRAD gradient surgery strategy originally proposed for multitask learning, and 4 state-of-the-art methods that we adapted to our framework. Our method was evaluated in the context of image classification and classic multi-domain datasets. We used an AlexNet pre-trained on ImageNet that we fine-tuned on source domains. We evaluated the accuracy of gradient surgery on ancient domains by holding one domain out for testing and using the remaining domains for training. We performed 20 runs for each combination of dataset, method, and held out domain. As we can see in the figure, agreement sum and agreement run outperforms other methods in PACS and Office Home in most target domains, and they are competitive in VLCS. Considering the mean accuracy and standard deviation across all domains, we see that gradient surgery methods perform better than the baseline and state-of-the-art methods in most evaluations. Moreover, within each dataset, agreement sum and agreement run outperform the other methods on average in PACS and Office Home, and they are competitive in VLCS. In this work, we study multi-domain gradient interference in domain generalization. We show that inter-domain gradients carry more conflicting information than intra-domain gradients. We propose 2 gradient agreement methods based on gradient surgery to deal with conflicting gradients. Experiment in image classification showed that gradient agreement improves generalization performance on ancient domains by reducing the gradient disagreement. The source code is available on GitHub. take a look at our project by scanning the code. Thank you very much.